right, hey, we are cranking out some videos here about series, infinite series in particular, and we've been talking about determining whether series converge or diverge. We've talked about geometric series, we've talked about using the integral test, we've talked about the comparison test and the limit comparison test. In this video, we're going to look at the alternating series test. Now, the alternating series test, as it is aptly named, we will only use for series that alternate. Now, way back in the first video on sequences, and I think we brought it back up when we talked about geometric series in 11.2 as well, we had a series of -1/2 to the n minus 1 as n goes from 1 to infinity. And this was a geometric series. And if we plugged in values of n, right, if n equals 1, I get a 0 exponent. And then if n equals 2, I get 2 minus 1, which is an odd exponent, so my term stays negative. And then we get positive 1/4 and minus 1/8 and plus ... So we can see in this particular example, this geometric series, we have r being -1/2, and since the absolute value of r is less than 1, this is convergent. But when the r is negative for a geometric series, we end up creating alternating signs in our series. So we have a positive plus a negative, plus a positive plus a negative, so on and so forth. So that's the conversation in this section, and it's about series that alternate in sign as we add them together. Now, some textbooks typically write the series alternating in a very generic form, something like this: -1 to the n minus 1, and then write a b sub n. Right? And Stewart in particular uses this notation. And what that does is that makes the first term positive, and then the second term is negative, and the third term is positive, and so on and so forth. So he's just denoting an alternating series in this generic form. All right. Now, if we look at our geometric series, we could write it that way, right? If I take a look at this geometric series here, kind of come down here, this is really like -1 times 1/2 to the n minus 1. And then we can write that as -1 to the n minus 1, and then 1/2 to the n minus 1. So in the language of the Stewart textbook and some other calculus textbooks, we see here's our alternating term officially, and then here's the b sub n term, the terms that don't alternate. So mentally, we're separating the thing that creates the alternation in sign, and then just the absolute value of the terms, right? The things that don't alternate. So that's our scenario here. Now, technically, the terms don't have to start out positive. I mean, they could start out negative. So you might see another textbook also write this is like -1 to the n b sub n. And so that causes the first term to be negative. Right? So I would have -b1 plus b2 minus b3. So on and so forth. And again, in a generic form, what we're doing is pulling off the thing that creates the alternation of the sign. And we're really looking at the absolute value of the terms. We're looking at the b sub n, right? The positive terms without the alternation of the sign of the terms. So we have alternating series, and that's what we're considering in this section. So we want to look at the alternating series test. So I'm going to go ahead and write out the statement of the alternating series test, and then I want to look at some examples, and then I want to justify what the alternating series test says, right, and why we have the conditions. All right, so if we have an alternating series, if a series alternates, and again, we can write, kind of in a generic form, -1 to the n minus 1 b sub n. And again, it doesn't really matter if the terms start positive or negative. What we're going to do is we're going to consider the b sub n's. We're going to consider really the absolute value of the terms, if you will. So first of all, if the terms decrease, right, so this says that the terms are decreasing, and if the terms go to 0, then the series will converge. Okay. Now we need both conditions to be met. We can't have just one and not the other. We need both conditions to be met. So the terms are decreasing and the terms are going to 0. Now, a lot of times students will ask a really good intuitive question here is like, well, if the terms are decreasing, doesn't that mean they go to 0? And, not necessarily, right? I mean, I could have terms decrease and go to a number that's non-zero. I don't want you to see that graphic yet. I don't want to come back to that in a second, right? Let me just plot over here, right? So let's say the terms have a non-zero limit. So I'm going to have the terms decrease and not go to 0, right? So anyway, so we need both of these conditions to be met. So since I went ahead and had that graphic there, let's discuss why we need both of these conditions. So I borrowed this graphic out of Stewart's calculus textbook. This is a cool graphic to look at. What this graphic is representing is the nth partial sum. So in other words, if I start at 0, I've added no terms at all whatsoever. Supposing the first term is positive, again, it doesn't really matter, but supposing the first term is positive, I'm going to add the first term and I get out here. I get to the first partial sum. Now, since they're alternating, when I add the second term, it's really negative here. So I'm really subtracting, right? And I end up somewhere back here. Now, I know that I'm going to end up with the second partial sum being positive because the first term was bigger, right? Because they're decreasing. So if my terms are decreasing, the first term is larger in absolute value for the first partial sum. And then when I add the second term, it is getting smaller. And so I end up over here, right? I have a positive second partial sum. And then I add the first term, so the first term is positive, and it is getting smaller, so I end up here at the third partial sum. And then I add the fourth term, which is going to be negative, and again, it is smaller, so I'm going to end up somewhere here, the fourth partial sum. And then this pattern is going to continue, so as long as the terms are getting smaller and smaller, then I'm going to add, and I'm going to kind of oscillate back and forth here. Get closer and closer. Somewhere the infinite sum lives between adding no terms together and just one term. And I can hone in, I can zero in on that term. Now, the terms also have to go to 0 in order for this convergence to occur. And the reason why is, let's suppose the terms decrease, but they approach 1. Then at some point I end up doing like +1 minus 1, +1 minus 1, +1 minus 1, and I end up kind of jumping back and forth, +1 minus 1. So the terms have to decrease and they have to go to 0. And if that doesn't happen, right, then my infinite series is not going to converge. So again, we're looking at the sequence of partial sums to justify the convergence here. Now here's another kind of cool way to visualize this idea of the sequence of partial sums. And again, this graphic was in Stewart's textbook, and I borrowed it here. It's a cool visualization. I didn't want to have to write this out by hand. So here's the list of terms in my series. Now notice that symbolically here, we're considering the alternating signs. Right, so we're not writing this as the b sub n. Remember, the b sub n is the absolute value of my series of terms. So this is the a sub n. This is the alternating. So we see, positive term, negative term, positive term, negative term, positive term, negative term, so on and so forth. So if the terms are decreasing, as we see here in absolute value, and they're going to 0, then the sequence of partial sums will alternate but converge. Right? So I get, plus, minus, and my sequence of partial sums is honing in on whatever this sum is right here. Now, if I scroll back up to the top, it's kind of the same thing here, right? We had the sequence of partial sums kind of jumping back and forth, and eventually we kind of zero in and land at the true infinite sum. So, again, in summary, in order for a alternating series to converge, we have to have the terms go to zero and decrease. Now again, we look at that in the absolute value. So as long as the terms go to zero and decrease as they alternate, we're going to bounce back and forth, and land. Right? We're going to kind of hone in on the infinite sum. So let's go ahead and take a look at an example. I'm going to come back to that alternating geometric series that we started off with. Now we had rewritten this series as -1 to the n minus 1, and then we had really like the absolute value of the terms, right? My b sub n was what we call this symbolically, right? So my b sub n is 1/2 to the n minus 1. All right, now since this is an alternating series, I can use the alternating series test. And in order to use the alternating series test, I have to show two things are true. I have to show that the terms decrease and that they go to zero. So let's take a look at the first one. So for the first one, right, if this is my b sub n, I have 1. I'm going to write this as 1/2 to the n minus 1. It's just going to be a little bit more convenient for showing this is true. And then the n plus 1. So think about this for a second. If I substitute n plus 1 into my sequence of terms, I get n plus 1 and then minus 1. So that's just going to be 1/2 to the n. So, I'm kind of asking the question, right? Is this true? I don't know if it's true. I want to see if it satisfies that condition. And, we should be able to see intuitively, right, that, 2 to the n is going to be a little bigger than 2 to the n minus 1. So 1/2 to the n is going to be a little smaller. Again, if n was 5, 2 to the 5th is 32. 2 to the 4th would be, 16, right? So that's definitely true. And I could take that same approach that I did back in the direct comparison test. I could multiply both sides by the common denominator and get to this statement. I should see that that's true as well. If that's not obvious, I could break up that exponential in that manner and get to this statement, and then I can divide both sides by 2 to the n. So if I divide by 2 to the n on the right hand side, I get 1. If I divide by 2 to the n over here, I get 1 times 2 to the negative 1, and 2 to the negative 1 is 1/2 to the positive 1. So I get 1/2, right? So I could take this all the way down to a point where I know it's true. So the positive values of the terms in this alternating series are decreasing. And then now we have to say, are they going to zero? So again, I'm going to say, limit of b sub n equal to 0. So as n goes to infinity, long term, is 1/2 to the n minus 1 going to 0, question mark. And, the numerator is staying constant, and this exponential term and the denominator is going to infinity, so these are definitely going to 0, check mark. So because we have met both of the conditions, then my series converges by the alternating series test. So thus, -1 to the n minus 1, 1/2 to the n minus 1, converges by the alternating series test. Right? And that is really what we're going to do. Now we just want to make sure, my series actually alternates. I can't use the alternating series test on something that doesn't alternate. I'm not going to get valid results there. So as long as my series alternates, this is one possible way to test the series. Now, just to point out to you, this series was geometric. I didn't need to use the alternating series test at all. It was geometric, and because the r value in absolute value was less than 1, right? The r was -1/2 technically, right? Then r being less than 1 tells me the geometric series is convergent. So when I look at a series, and again I've mentioned this in some prior videos, when I'm looking at a series and I'm trying to determine whether it converges or diverges, I'm going to have a flow chart. And I'm going to ask myself, which technique can I use? And the first thing we talked about in the 11.2 video was the test for divergence. So I'm actually going to look at that first. That's going to be the first thing in my flowchart. And then I'm going to ask, is this geometric? Because if it's geometric, I get a nice clean result from that. Then I can consider the integral test, I can consider the direct comparison or limit comparison test, and now I have the alternating series test as another tool in my, infinite series bag of tools. Now again, in my flow chart, which one am I going to choose? Well, obviously if the series is alternating, I can't use the comparison test because that required my terms to be positive. And I can't use the integral test because that required my function to be positive as well. So if the series is alternating, I typically would use the alternating series test, again, unless I notice that it's geometric. Let's take a look at a different example. So in this example, I want to look at something that's divergent, and I want to talk about, kind of the technical way we're supposed to approach this. So I just told you that the series was divergent, typically in a set of homework problems, or, in something we're doing in the real world. We don't necessarily know that the series is divergent or not. So I'm telling you that it is. Let's see what happens, and let's talk about how we officially deal with this. Now we can see we have this alternating term here. We have the -1 to the n alternating term. So my b sub n, right, kind of the absolute value of the terms here, is 3n over 4n minus 1. So we have to ask the first question, do these terms decrease? And, question mark, right? So I'm looking in this case at the n plus first term is going to be 3 times n plus 1 over 4 times n plus 1 minus 1, and I'm asking, is this less? Now, the way we've been dealing with these up to this point, we've been simplifying this through algebra. So I want to keep going through that work. Let's simplify this through algebra and see what we can achieve. So remember, I am going to multiply both sides by the common denominator. So I take this denominator, multiply it to this denominator, and then I multiply both sides by that term. It's how I like to think about this. So on the left-hand side, the 4 times n plus 1 minus 1 is going to cancel. So I'm left with the numerator here of 3n plus 3, and then 4n minus 1. That was what didn't cancel over here. Right? And then is that less than or equal to? So when I take this term and multiply on this side, the 4n minus 1 cancels, and I'm left with 3n times, and then I have the 4n plus 4 minus 1. I'm just distributing the 4 here to clean that up a little bit. So then on the right hand side, let me distribute. The 3 times the 4 is going to get 12n squared, and then 4 minus 1 is 3. So 3 times 3n is 9n. And then I got to FOIL this thing out. So 3 times 4 is 12n squared. And then if I do outer, I get -1 times 3n is -3n, and then 3 times 4n is positive 12n. So I get 12n minus 3n is 9n, and then I get minus 3. So let's see, I can subtract 12n squared from both sides. That's going to go away. I can subtract 9n from both sides. That's going to go away. And I'm going to get -3 is less than or equal to 0. And that is a true statement. So the terms are decreasing. So we've met that condition. Now I told you this diverged, so that must mean the second condition fails. So let's look at the limit of b sub n, right? And does that equal 0? So my b sub n again was 3n over 4n minus 1. Look long term. Do these terms go to 0? So, I like L'Hopital's rule, right? I get infinity over infinity here. And with L'Hopital's rule, I get that the derivative of the numerator is 3, derivative of the denominator is 4, and that is not 0. Okay? So I'm not meeting the second condition. Now look, technically this is not prove divergence. It tells me that it doesn't converge, which, all right. in all intents and purposes, that means that it is diverging. But what you're going to always see in a solutions manual, and what we really should do in a valid manner, is use a different test. So I'm gonna come back here and I'm gonna retest my series in a different way. And usually the way that we're gonna do this, I'm gonna say pretty much always the way we're gonna do this is we're gonna use the test for divergence. Now remember, the test for divergence basically says if the terms don't go to 0, then the series is diverging. Now we've really kind of already done the work for that, right? So from our work above, the limit of the b sub n's went to 3/4. Right? So what that means then is when I throw that alternating term on, 3n over 4n minus 1, that's going to go to, and I'm going to write this as plus or minus 3/4. So this is non-zero, right? I'm going to plus 3/4 minus 3/4, plus 3/4 minus 3/4, plus 3/4 minus 3/4. Right? Again, visually, plus 3/4 minus 3/4, plus 3/4 minus 3/4. So long term, I'm not going to 0. So by the divergence test, right? So I'm going to say the series diverges by the divergence test. Okay? All right, so there's an example of where we see convergence, and then here's an example of where we see divergence. All right, I want to look at a couple more examples actually. And the next example I want to look at is actually really cool. It's kind of contradictory to what we might think intuitively based on prior knowledge. So what I want to do in this example is I'm going to look at -1. Whoa. What's happening? I want to look at -1 to the n minus 1 times 1 over n, as n goes from 1 to infinity. So this is, 1 over 1, right? And then minus 1/2, and then plus 1/3, and minus 1/4, and so on and so forth. Now, if we think of the b sub n that we have here, the b sub n is 1 over n. So if we think back to prior knowledge, that is a p-series that is divergent. So p equals 1, right? My exponent is 1 over n to the 1, so that is a divergent p-series. P is less than or equal to 1. So I might think, intuitively, based on prior knowledge, that this series would diverge like a p-series, and it actually doesn't. And if we use the alternating series test, we will quickly see that. So do the terms decrease? So I would have 1 over n plus 1, is that less than or equal to 1 over n? And again, we can see this is true, right? Numerators are the same. The left-hand side has a denominator slightly bigger, so the fraction is slightly smaller. If I do my algebra, I definitely get to a point where I see that they are decreasing. And then the second question being, or a second condition being, do the terms go to 0? And we can see, oh man, come on, fingers work for me, please. We can see that, 1 over n then goes to infinity, that's in essence 1 over infinity, and that goes to 0. So we get that to match as well. So what's really interesting here is that the non-alternating 1 over n is a divergent p-series, but the 1 over n as it alternates is actually convergent. So when we throw the alternating term on in this scenario, it creates a convergent p-series. Now this series is so frequently used, it's called the alternating harmonic series. So that's a nice example to look at. And we have an alternating harmonic series. So you will see this again. So my alternating harmonic series is convergent. Yeah, and look, I made a mistake here and I wrote in power. Remember, it doesn't matter if the first term is positive or negative. Okay. So the p-series 1 over n, as it alternates, is called the alternating harmonic series, and that is convergent. Okay, so kind of cool. kind of cool example to see comparing back to prior knowledge. So last part of our conversation here, let's talk about if we have a converging series and we estimate it with a partial sum. So let's say we sum the first 10, 20, 30, 40, 50 terms, whatever. What would be the error from that estimation? So let's go ahead and write what the statement is in general, and then let's apply it back to, let's go back to the alternating harmonic series, and we will apply it to that. So basically, we say something like this: for a convergent, let's say for a convergent alternating series, I'm going to say, -1 to the n minus 1 b sub n. And again, whether that first term is positive or negative doesn't really matter. So for a convergent alternating series, the remainder of using the first n terms, right? So let me say s sub n, the nth partial sum has error, and it's a max error actually. So it has error, remainder r sub n, and that is at most the first unused term. So notice I'm putting the remainder in absolute value, and it is at most the first unused term. Now what does that mean, and why is that the case? So if we write out, like the terms of the series, so say I have b1 minus b2 plus b3, say minus b4 plus dot, 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 dot. Let's say we come to the nth term, and then we have all of the remaining terms, so on and so forth, and plus 2 there. Now, if we're summing up the first n terms, here's my s sub n, right? And all of the rest of this is the error. Right? This is my r sub n. Right? Now again, that is an infinite series. We technically can't determine the sum of the infinite series unless it's geometric. Right? But considering it's not geometric, otherwise we would use that result. So if this is not geometric, right, what is happening? What is the error? Now, just like that picture that we had back in the beginning, this one right here, so as the terms decrease and go to 0, right, the sums are going to just continue to oscillate back and forth, if you will. So if I look at the first term, when I subtract the next term, that's even smaller. And then I add the next term, and then subtract, and so these sequence of partial sums keep getting smaller and smaller and smaller. So when I look at all of these remaining terms that I have here, starting at b sub n plus 1, as I add more and more and more and more, that sequence of partial sums oscillates back and forth. But the largest of that error can be is this first unused term. Because I add more and more, I hone in on the actual value of that error number. So the error then is less than or equal to that first unused term. Now we could improve that error by looking at the sum of the first two terms, right? And then so on and so forth, right? But it's kind of a raw, dirty calculation. That first unused term is the max error. So to take a look at, applying that, if we look at that alternating harmonic series, so let's take a look at that alternating harmonic series. And we have, again, the b sub n was 1 over n in this case. So let's say we sum up the first 50 terms. So we're going to estimate, let's say we're going to estimate the infinite sum, right, with the sum of the first, let's say 50 terms, right? And let's determine the error. What is the error? What is the max error? So I'm gonna lean on technology to calculate the sum of the first 50 terms. And we've done this in the past, but I just want to remind you how I would do this with technology. So on the TI, I'm going to do math. Where's it at? Math, and I'm going to punch number 0. It's going to begin this sum. And I'm gonna use the letter N just because that's typically what we use. So I'm already in the alpha locked mode. So I'm gonna just come down here and type N. N's gonna go from 1 to 50. And then I'm gonna type in my formula. So I'm going to use parens here, and I'm going to say -1 raised to the power of, and I got to do alpha n minus 1. And let me come off the exponent. And then we had 1 divided by, and I'm going to do alpha n. So calculator will add the first 50 terms of the alternating harmonic series, and there is that value. All right, so we have S of 50, so the sum of the first 50 terms is approximately that value. Just as a reminder as well, there's a couple other web-based tools that can do this for you. You could just Google search, infinite series. You'll probably find a calculator out there. I'm going to go ahead and use Desmos. So with Desmos, I don't know if you can see this. There we go. I can type sum, S-U-M, and I say n goes from 1 to 50. And then very similarly, I will do -1 and then raised to the power of, so I'm using my caret key there. Uh-oh, why didn't you stay up there? Minus, and you know what I think I got to do is put parentheses, and there we go, and -1, and then times 1 divide by n. Well, actually, that's correct the way that I wrote that. Right? I'll put parentheses just because this is how we actually wrote it. Right? So there is the sum of the first 50 term, just what we got with our TI. Now, the estimation theorem for the alternating series test says that the error from this, right, so the error, the remainder of the first 50 terms, is going to be, so I'm looking really at the absolute value. Right? So this is the absolute value of, the 51st term. Now, I don't really need absolute value here. And the reason why is I'm writing the B sub n's, right? So, and the B sub n's are the positive values. Now, for this case, this B sub n is 1 over 51. Right? My B sub n is 1 over n, so that's 1 over 51. So that is the max error from that approximation that we got. And if I plug that into a calculator, I get 0.02. Okay? So the remainder of the first 50 terms is at most 0.02. Now again, as a reminder, it doesn't really matter if the series start with negative or positive in regards to the error that we get here. The error will be the same. The error will be an estimate of the first unused term in absolute value. Error will always be positive. Now, if the first term starts off negative, that definitely can change the sum of the first 50 terms. And again, the reason for that, let me scroll back up to my visualization of the sum. Right? The reason for that is, as my terms alternate, I'm jumping above or below, or above or below, or above or below. So the summation can change based on whether the first term was positive or negative. So if you think about the infinite sum being right smack here in the middle, right, here's my infinite sum S. So if the last term was added, I'm going to be above the actual sum. It's going to be an overestimate. And if the last term in my estimation was negative, it was subtracted, I'm going to be below. I'm going to have an underestimate of my sum. So whether that first term is positive or negative will change the sum of the first, in terms that we're using. So, just to show you that, if I bring up my calculator again, I'm going to do second enter, and I'm going to hit my left arrow, and I'm going to make the first term be positive. So if I have -1 to the n, the sum of the first 50 terms is now slightly different. We see that it's negative 0.68, right? So it's changing the sign of my term. So this would be the underestimate of my summation in that case. All right, now let's say we come back to this problem and we're asking how many terms do I need to find a specific prescribed error. So let's say we're asking how many terms should we add, or should we use, should we sum to have my error let's say less than 0.0001, something like that. Right? Now, for the alternating series test, remember, for the alternating series test only, I am looking for the first neglected term, the first unused term. So the way that I like to write this is I say, I'm finding the term that is smaller than 0.0001. And in this case, the b sub n we have is 1 over n, and I want that to be less than 0.0001, and I'm just going to solve this inequality. So I multiply the n to the other side and then divide by the 0.0001, and my n has to be bigger than that value, and that value being 10,000. So my n has to be greater than 10,000. That's the way that I like to look at that. Now again, if I think about the first unused term is needing to be smaller than 0.0001. So if I were to kind of like guess and check, right, which this really isn't valid, I never want to guess and check. The alternating series test is never this simple in form. I want to say the alternating series that I'm using is typically never this simple in form. But if I look at like n equals 9,999, 9,999, and then I look at n equals 10,000. So there's the 10,000th term, and then there's the 10,001st term. So if this was my first unused term, I'm not smaller than 0.0001. I'm not right. Tenths, thousands, tenths, hundreds, thousands, 10,000s, right? So this term is 0.0001, but it's not smaller. So I need to go out to the 10,001st term. So this is saying n has to be bigger than 10,000. So I need to go out to the 10,001st term to have an error less than 0.001. So we're going to use up to n equals 10,000 terms, and then my first unused term will satisfy my error requirement. All right, I think that's everything I wanted to talk to you about in 11.5 alternating series test, and the estimation theorem. I will see you in the next video.